sends it down to the allocation unit, which is where we do the renaming of registers and scheduling out to the execution unit, which is the top half, which is the in-order version of the machine. And down below, you have the out of order, where you have the scheduler and the different execution units, which then is like a superscalar system where multiple execution units run in parallel. And have the memory down there feeding both the instructions and the data to all the different units up there. So on top of what we just saw, in order to gain performance, Sandy Bridge made changes to each of these individual units. So starting with the front end or the in-order portion, the major change that they made there was to add UOP decoded cache. So traditionally, we would want both the front end and the back end of the machine to be balanced so that you can get better performance from the machine. And with Intel x86 being a variable length instructions, decoding of instructions are really, really hard, especially if you have multiple prefixes on top of the instruction output bytes. So with this UOP decode cache, what Intel was trying to do was essentially cut down the latency for decoding these instructions. So what they did was add a new cache which stores all the decoded instruction bytes from the cache. So with this, they were essentially able to turn off the traditional front-end pipeline which does the fetching and the decoding of instructions. Instead, so this works, the cache works like any other instruction or data cache, and it basically relies on the temporal spatial locality that when you do a particular instruction, the possibility of you doing it again in the future is more. So essentially when you put it in the cache, you take the benefit out of it, and when you have a cache hit, your latency is vastly improved. The next feature that they added to the memory cluster was to basically support multiple loads in a particular cycle. So in Nehalem and earlier generations, you only had one load code and one stored code. So in a cycle, you at most could do one load and one store to memory. Whereas in Sandy Bridge, they added two load codes, so you could basically do two reads and handle one write to memory at the same time. And the out-of-order execution cluster was kind of completely rebuilt from scratch because they had to support this new AVX instruction set. I'll go into detail as to what they did there, but in a sense, this was they introduced the concept of physical register file. In Nehalem, we had the reservation station and the raw out-of-order guy storing data, the source data and the result data, and the basic data was duplicated in multiple places. But the introduction of the physical register file, they basically removed duplicating all the data and only resided it in one particular spot. So going into a little bit more block diagram details here. In the earlier slide, you read that Sandy Bridge essentially worked off of the Nehalem microarchitecture. So this is the Nehalem front end, which in itself was really fantastic. It had the 32K cache, it had the reading branch predictors, it could decode 4 instructions per cycle, and Nehalem introduced the concept of fusing at a macro instruction level, like a compare and a jump, and also at a microcode level where you could fuse multiple UOPs to gain better throughput and better latency. So on top of this, what Sandy Bridge did was add this UOP cache, which basically the main performance was to lower the power and get higher performance. And by doing so, what they did was they had to go back and revisit the branch predictors and improve the prediction methodology. They basically added more storage so that they could predict better. And the cache at the same time, as you said, if there's a cache hit, the left-hand side, all the yellow block, which is a traditional front-end decode, is all bypassed, which essentially gives you a better latency and it saves a whole lot of power. The memory cluster, this is again a basic Nehalem memory unit, which has one load and one store data, store address pose. And the memory cluster in Nehalem was good enough that it could handle misaligned cases. So if you're accessing memory that's not aligned in a 16-byte boundary or something, the hardware essentially takes care of all this stuff there. And Nehalem had store and load buffers to basically forward data between loads and stores. So on top of this, what Sandy Bridge did was add an additional load code so that we could do 2 reads per cycle. And at the same time, they overload it, the load and the store address goes together so that the bandwidth for the store address also increased by 2. And some of the benchmarks basically said that many applications, when it does 2 loads per cycle, really performs better compared to doing 1 load per cycle. So this is again the Nehalem version of the execution unit. You have the scheduler and the buffer, reorder buffer. The scheduler basically had the source data for all the instructions. The reorder buffer had the final result of the instruction. And it had all these execution units. So SSE here stands for SIMD Streaming Extension. And it basically is used for instructions for graphics and media processing. So you have this multiplier, integer unit, the shuffler, and logical unit, and all that stuff. But Nehalem basically dealt with data that's only 128 bits long, so which is a change for Sandy Bridge when they introduced the AVX architecture. So in order to accommodate that, what they did was introduce a concept of physical register file, which was present during Prescott and P4 times. So they brought that back so that they could basically get rid of duplicate data that was present in all of the other areas. And with this, the final data and the only data that's present is only in the register files here. And as I said, they increase the size to support AVX. They increase the size from 128 bits to 256 bits, which essentially gave them 2x. The AVX 256 bits essentially gave them twice the number of flops per cycle that they could do with the vector applications. So this is what I've been talking about, the AVX. So this is mostly used for graphics and media applications. There's a new set of instructions. It not only increases the size of the data from 128 bits to 256 bits, it also adds a new set of capabilities like broadcasting data across different pieces, doing masked loads and stores. Another cool thing is the notion of non-destructive source syntax. So traditionally, the IL32 has always been instructions that deal with 2 registers. And if you're doing add of A and B, you basically get A equaling A plus B. So essentially, you lose the A register, which is destroyed. Whereas here, with non-destructive sources, all the instructions are capable of dealing with 3 registers. So you could do A equals B plus C. So the software folks prefer such a syntax, and with AVX, we introduced that in Sandy Bridge. So putting this all together now, we basically had the basic pipeline to which you added the cache, you added the additional ports, you added the physical register file, and then the AVX to support 256 bits. So this is pretty much what Sandy Bridge microarchitecture is. So apart from all the core changes, they also had to deal with power management and to basically get a better performance and support various form factors. So for power management, they had to work with the constraints basically provided, and they had to work within those constraints. The constraints could be from how the CPU, what the CPU is capable of handling, what the platform specifications are, what the software and operating system user controls are, and different workloads and usage models. So the architects, when they dealt with the power management architecture, they had to consider all of these things and deliver something that's really, really good. Another thing is, since it's a converged core, there's also the factor of how best to accommodate the different features to support different segments. Like for mobility in the laptops, they have to be concerned about the form factor, the improved battery life, and stuff like that. So they have enhanced C stage. C stage is pretty much the idle stage in a processor. So whether you go to sleep or hibernate and stuff like that. So with the C stage, the power management, the architects basically develop a new methodology that basically could wake you and bring back up from sleep very quickly compared to old generation processors. And they work with several OEMs, which are who are the original electrical manufacturers, to work around the form factor regarding the thermal constraints and other mechanical constraints. So in summary, I just want to wind up here. I'm not going to go into details about the graphics and other stuff. So Sandy Bridge is a very good nanometer process. It has very good enhancements. And somebody, I think at Tom's Hardware, termed it as the best processor out there right now. And no competition can even come close to matching Sandy Bridge's performance. So I think that's all prepared slides at hand. And yeah, I just wanted to say that our team is actually, in fact, hiring. We are looking for people who are interested in doing P-code and microcode development. We are interested in people doing software tool development and power and performance modeling. Actually, I'll go over responsibilities and qualifications. So, as far as the performance modeling is concerned, we're looking for people who can do work in areas such as the actual CPU code itself, modeling of I/O, modeling of different interconnects, the graphics modeling. This is all done in software. And there's also a software team specifically looking for software engineers who can develop performance modeling too. Like you can develop an entire simulator to basically simulate all of the instructions and architecture. And finally, our team is looking for developers for microcode and P-code. So in terms of qualifications, we're looking for people who have done their master's or PhD degree and have good experience in computer architecture, operating systems, power management, and probably C, C++ is a benefit to have, and any scripting language like Perl or anything will be beneficial to have as well. That's all I had. Any questions?
So our group has 20 openings.
And that's just these two hiring
For our
managers.
group in Boston, Massachusetts, and Portland, Oregon.
Yes.
Out of curiosity, why did Sandy Bridge decide to go with dual channel, whereas Halo supported triple channel on the assets?
I'm sorry, what did you say?
Why did Sandy Bridge decide to go with dual channel DDR3, whereas the previous in the Halo architecture, they supported triple channel for i7? It seems kind of backwards.
It basically has to do with bandwidth that you get from supporting dual as a triple channel. And with the Sandy Bridge architecture, with the graphics also in the core, and it's everything integrated into one package, that's better to basically wind down rather than go that scale back up.
Well, I saw this news from a lot of places that said Sandy Bridge has a digital environment model inside it.
Sandy Bridge has
What environment? So basically, a lot of places that I see this news will say Intel has some kind of collaboration with the content provider like Disney or something. So if you buy the Intel Sandy Bridge chip, then you can enable the video from those content providers for some kind of channel that run on processing. If you don't buy the Sandy Bridge, then there is I don't know, but I see this news. I cannot find the technical details.
So Sandy Bridge has worked with video content providers to basically better security with DRMs and stuff like that. They have new security algorithms to efficiently provide streaming movies and content to your laptop. So I don't know whether you're referring to that or is it something else that I'm missing? Sure. You have questions?
I think I'll just following what you said. I think you were talking about there was kind of like something called Intel Insider. It's basically like a DRM management for the processor itself. I don't know what you meant, but
Okay.
like it's kind of like vague details about that.
Yeah, I mean, Sandy Bridge has like new algorithms, as you said, to support DRMs and better securing all the digital content that the movie providers provide. So it's additional security to basically make sure that it's not easily ripped off from your system when you're doing it online streaming movie or videos or whatever.
Really is not clear here is for the